Everyone, I want to do a quick example here for objects colliding and conserving momentum. This is kind of like the LOLs used in energy, but now we're using it for momentum. Instead of the bar graphs going up to tell you if you have momentum or not, this time the bar graphs are going left and right. The zeros in the middle, there could be momentum to the right, which will be positive, and momentum to the left, which will be negative. So I'm going to do two examples here for you, show you how the momentum LOLs will work, and set up the equation and solve for what you don't know. Okay, so this is our scenario. I've got two carts, cart A and B. A is moving towards B. B is at rest. B is bigger than A, and then that little orange thing there is the collision. So the collision happens, and cart A bounces backwards. So the question is, what happens to cart B? Which way does it move, and how fast is it moving? And that's the power of conservation of momentum. So in the graph here, what I want to do is look at the before scenario and the after scenario. So to give you some values here, let's have object A be 2 kilograms and be moving at 2 meters per second. And object B, let's give it a mass of 4 kilograms, and we obviously know it's not moving because I drew no arrow on object B. So that's the before scenario. What I have to do now is show how much momentum I have in my bar graphs here. So for the first object, to find momentum, all you have to do is do m times v. So in this case, we're going to have 4 units of momentum for cart A. And I can show that by having a bar graph that is 4 in the positive direction. For cart B has no momentum because it's 4 kilograms times 0. And so I'm just going to put a little x on the 0, knowing that there's no momentum whatsoever. You can draw nothing if you want. Whatever helps you know that there's no momentum. So the beginning momentum must equal the ending momentum. And if I look at my scenario here, it looks like cart A is moving backwards. So I know the mass of cart A after the collision is still 2 kilograms, didn't lose any pieces. And let's say it drifts backwards at 1 meter per second. The question would be, what's going on with cart B? For cart B, it's still 4 kilograms, but what I don't know is VF. I don't know its final velocity. So if I want to make my LOL for cart A, to do the momentum LOL, I've got to do 2 kilograms times negative 1 meter per second, which is going to give me momentum of negative 2. But since momentum is conserved, I had positive 4 units of momentum in the beginning. That means I have to have positive 4 units of momentum at the end. So if you see a negative unit of momentum for cart A, that means cart B has to have momentum in the positive direction to cancel out that negative momentum backwards. So now I've got my LOL here. I know already that cart B is going to move forwards after the collision. The question is how fast. So now we need to set up our equation. And to do this, the initial momentum must equal the final momentum. So the initial momentum was mass of A times velocity of A plus mass of B times velocity of B equals mass of A times velocity of A final plus mass of B times velocity of B final. And that's how you set up a conservation of momentum equation. If these objects combine together, we know that they would hit and stick, and we can actually add their masses and say they move at one combined speed. We'll do one of those in another example, but in this example, since they are separate in the beginning and separate at the end, keep the equations separate in the beginning and at the end. Put it in your values here. We knew that this was 4 kilograms meters per second in the beginning. Cart B had no momentum, so 4 must equal 4 in the end. And for cart A, after the collision, it had negative 2 units of momentum, and cart B had 4 kilograms of mass, but we don't know its final speed. And if you look at my equation here, the only unknown is final speed. So let's do the math. So I've got to move that negative 2 to the other side, so I get 6 kilograms meters per second as my momentum. I have that equal 4 kilograms times V final. To find V final, I'm going to divide by 4 kilograms. And when I do that, the kilograms are going to cancel, and my answer is positive 1.5 meters per second. So I know after the collision, cart B must be moving to the right with this velocity. And that's as simple as a conservation of momentum problem can be. You look at the momentums before, you look at the momentums after. The LOL helps you write the chart, and you solve the problem. Let's have something stick together. So here we got the same cards again, but this time when A hits B, their bumpers kind of mash together, and they now drift as one mass. So the question is, when card A hits card B and they move together, what's the final speed of both of them together? So again, identify the objects. Object A has 2 kilograms, and let's give it that same initial 2 meters per second of speed. Card B is still 4 kilograms, and it's sitting still with 0 velocity. So if I was going to do my LOL, card A has momentum to the right, and card B has no momentum. So after the collision, we said they're moving together. So when I identify after the collision values, 2 kilograms, but I don't know its V final. Same with card B. Card B is 4 kilograms, and I don't know its final velocity. But looking at my LOLs here, I can see that my initial momentum was to the right. So I have to keep having momentum to the right. So B is going to have some forward momentum, and A is also going to have some forward momentum. So now let's write our equation. So our equation in the beginning was, again, MA times VA initially, plus MB times VB initially. And I can keep those separate because the objects were separate in the beginning. After the collision, the two objects were smashed together. So there's 2 ways I'm going to write this. I'll write it one way, and then I'll show you the other way you can write it. You can say MA times VA final plus MB VB final, as long as you remember these 2 velocities are the same value. Or, since the masses combine, I could add the 2 masses and multiply by their common VF. So now let's put our values in. The first, MAVA, in the beginning is still 4 kilograms meters per second, based on the values I gave you. Card B had no momentum, so I can just add 0. After the collision, they were stuck together, so they have a combined 6 kilograms times their combined final speed. If I want to solve for VF, I'm going to divide by 6 kilograms. See the kilograms go away again, so 4 divided by 6 gives me my final velocity. So VF equals 0.67 meters per second. And that is the combined speed of those 2 objects moving together. So now start working through these in your workbook, and good luck.